Good morning, everyone. Well, at least it's morning while I'm recording this. What we're going to be doing in the next couple of chapters is actually doing a very, very quick synopsis on water and carbon. And I know it's like, wow, why do we have two whole chapters devoted to, these compounds and elements? Simply because that's what makes life possible. It's really important to understand the properties of water, just in general, and the properties of the element carbon. And by understanding those, we'll be able to understand some of the more fundamental mechanisms of what makes life possible. So let's just jump into water, which I think is probably going to be a pretty quick discussion here. So, water is the biological medium on Earth. In other words, all living things, plants, animals, everything needs to have water either surrounding them, like animals that actually, or organisms that live in the water, or within them, like we do, right? We kind of take our water with us in our circulatory system. So water is absolutely essential for life processes, chemical life processes. Most cells, which are the smallest units of life, right, are surrounded by water, and cells themselves are about 70 to 95% water. Now, if you think about the human body, on the inside of our bodies, it's pretty wet, right? I mean, we have lots of water in our fluids, blood, all that stuff, right? The cells that are on the very outside of our body in your skin, you might be asking, well, they're not really surrounded by water, but they're actually not alive, right? So they're dead cells on the surface of your skin. The only real living cells you can see from the outside of your body are in your mucous membranes, right? So eyes, inside your mouth, nose, that kind of thing. So those are, as you can tell, in a wet environment. So the abundance of water is the main reason the Earth is habitable. Okay, and what we're going to be doing is talking about why that is. So the water molecule, remember from the last chapter, is a polar molecule, which means one side of the water molecule, the oxygen side, is negative, and the hydrogen side, the opposite side, is positive, right? This polarity allows water molecules to form hydrogen bonds, these temporary little weak bonds that you see right here, these little dotted lines, right, that go between the positive hydrogen and the negative oxygen. Opposites attract, right? So it's again, it's more of an attractive force than it is actually forming a bond or sharing electrons. So that is really important. It actually has a lot of consequences for life. So, what we're going to be talking about and what the polarity of water allows to happen is cohesiveness. Water is actually pretty sticky to itself, right? So that means, it forms droplets and it can actually, sort of travel in groups. Water molecules will travel in groups because they're all attracted to each other. Water also moderates temperature, right? It regulates the temperature on the earth, in the oceans, actually in our bodies. Any mass of water is actually, it's kind of hard to change the temperature. It takes a lot of energy to cool it down or heat it up, right? So that's really good, and it allows those temperature moderations. Um, it expands upon freezing. So when water freezes and turns to ice, it is actually less dense than the surrounding water, and that makes it float. And because it's polar, it is a very versatile solvent. And if you don't remember this, but a solvent and a solute are two different parts of a solution. If water is the solvent, what that means is it can dissolve lots of biologically important molecules, salts, sugars, hormones, fat, or not so much fat, but proteins. All of those different molecules can then flow either around a living thing or through a living thing, since we just said water is really important to cells. Okay, so let's talk about cohesion first. Collectively, hydrogen bonds, right, that little stickiness that each water molecule has towards each other because of that polarity, holds water molecules together, right? So that's called cohesion. Now you can see right here, this little pond skater on the surface of a pond here. It's not sinking in the water. You can see its feet is kind of causing like these little dimples. You may be asking, why 4 feet? Well, there's actually two small legs that are kind of like tucked up under the body in the front. Um, this allows animals to, utilize that surface tension. There are all kinds of insects and other things that will float on top of the water, never actually breaking the surface. Okay, so that's what, pardon me, surface tension is. Cohesion also helps water flow up and down the inside of plant stems, right? So if you think about it, you have a 300-foot tall redwood tree in, the Pacific Northwest. How does the water go from the roots all the way up to the leaves at the very, very top of the tree? Well, the stickiness of water kind of holds it together as it goes all the way up the tree. Now, there's another sort of uh, term here that is not really the same as cohesion, and that's called adhesion. So you can see that right here. The adhesion of water to plant cell walls helps to counter gravity too. So there's a slight difference here. Cohesion is where water molecules will stick to each other. So that's just all water. That's all we're talking about. Adhesion is where water can stick to other substances because of its polar nature, right? Not every, not the only polar molecule in the world isn't water. There's lots of other polar molecules too. So if you think about it, when you get in the shower and then you get out, it's not like you're dry. It's not like the water just, kind of like tumbled off of you like a newly waxed car, right? Um, the water will stick to your hair, your skin, and all that stuff. Well, that's because the water is literally attracted to your body through these little hydrogen bonds, right? So there's a temporary little attraction there, and that's why things, stay wet when they get water on them. Okay, so the moderation of temperature is important. Water absorbs heat from warmer air and releases stored heat to cooler air, regulating the temperature. This is, I think, probably most evident down the shore if we're talking about on the grand scale of things, right? We could also talk about it on the small scale too, but if you think of the shore, it's a little cooler in the summer. That's why everybody has, shore houses down there so they can escape the heat from the mainland, from inland, and it's a little warmer in the winter. This is why, we don't, back in high school, you didn't really get a ton of snow days in New Jersey because we have the warm, relatively warm Atlantic Ocean right off the coast. That warms up the air, and a lot of times we'll get wet snow or rain as compared to a very cold, fluffy snow like further inland in the United States, like North Dakota or something, right? So the specific heat of water of they're calling it a substance here, but of course we're talking about water. Whoops. Is the amount of heat that must be absorbed or lost for 1 gram of that substance, so a very, very small amount, about 1 milliliter if you're talking about water, to change its temperature by 1 degree Celsius. Okay, so in other words, this is a measure of how hard or easy it is to change the temperature of water, right? So it actually kind of takes a lot of heat to change the temperature of water or cool it down. Think about like, the last time you put a pot on the stove to make a pot of mac and cheese or something like that, right? So you put a pot of water. Seems like it takes a long time and a lot of heat for that water to boil. Conversely, if you fill up your ice cube tray and you stick it into the freezer, kind of seems like it takes a really long time at, -5 degrees or whatever in your freezer to freeze, right? Well, this is because water has a very high specific heat, and that's the evidence, right? It takes a really long time and a lot of energy to change its temperature either way. Now, if you think about human beings, we have about 5.5 liters of blood, and about half of that is water in our systems. You don't want your temperature changing immediately. Like you want to have a little bit of lag time. So like think about it last time you went into your hot car in the parking lot. If you don't have like those sun shields and stuff on your windshield, your car can be 130 degrees inside, even warmer. You don't want your body temperature automatically go 130 degrees. That would be also awful. So what regulates that is the large amount of water we have in our bodies. It takes a lot of energy to change the water temperature significantly. Okay, so water can absorb or release a large amount of heat with only a slight change in its own temperature, in other words, right? And that minimizes fluctuations in living things, which is a good thing. All right, so if you look at the shore here, now this is the Pacific coast in California. The water itself might be, somewhere in the 60s, which is going to cool down the coast. San Diego, Los Angeles, Santa Barbara are all in the 70s. But if you go, I don't know what, 50, 80 miles inland, right? The temperature creeps up really, really quick. And you can see here, Palm Springs, California is 106 degrees, right? It's like a 40-degree difference between, or 30-degree difference anyway, between the coast and the inland, right? So that's kind of showing you how well water can regulate temperature. And at night, in inland, interior of California might actually drop down below 72, but the ocean will keep the coast relatively warm. Okay, so evaporative cooling, I know it's kind of a gross picture, but is transformation of a substance from liquid to gas. As liquid evaporates, like water does all the time, its remaining surface cools, a process called evaporative cooling. So when we sweat, right, when water literally seeps from our skin, inside our skin onto the surface of our skin and evaporates, what it does is it pulls a little bit of heat away from our bodies, right? That's the energy it uses to actually turn from a liquid to a gas, in other words. So evaporative cooling of water helps to stabilize temperatures in organisms, right? We want to always keep our optimal temperature. For us, it's 98.6 degrees. If we get too hot, we sweat, right? And also bodies of water. So as the surface of the ocean evaporates, or a lake or a river or something like that, it will actually cool the water down as well, right? So I think that that's an important concept too. Ice is actually a really good insulator, okay? And because it's less dense, it will float on the surface of a body of water. So in the wintertime when the lake freezes, right, the ice doesn't go to the bottom, it goes to the top. Ice floats in liquid water because it actually expands. It becomes less dense as it freezes, which is opposite of a lot of other different types of compounds. A lot of compounds actually get more dense when they freeze. But because ice does this, it acts as a layer of insulation, right? So it protects the rest of the water from the super cold air up above, and actually acts as kind of like a blanket, right, over a body of water, a lake, or sometimes even the ocean if it gets cold enough. So what that does is it protects all the organisms below the level of the ice. Now, of course, the water is going to be really cold, but it's not going to be frozen, right? So the cells that make up an organism, like this little shrimp right here, what they'll still be able to do is use water as it was intended by life, right? As a solvent for moving molecules of different things around their bodies or through their bodies. So I think that that's an important concept too, is that ice actually acts as an insulator, protecting living things below the level of the frozen water. Now, as we said before, water is the solvent of life, right? A solution is a liquid that is homogeneous mixture of substances. In other words, it's evenly mixed, top to bottom, left to right, up and down, right? So um, the solvent is what dissolves the solute. Okay, so in other words, and I'll just say it like this: every time we talk about a living thing, the solvent is going to be water, because water is absolutely critical for living things to survive, and that's what's dissolving all of those essential chemicals, allowing life to be sustained. Okay, so water is a very versatile solvent because it's polar. It sticks to lots of things because of those hydrogen bonds, and that means it can carry things around with it, like, all the stuff in our blood. If you have gotten a blood test recently and you actually wanted to see the readout, there's a bajillion things that you can isolate from the blood, because all of those compounds are running through every cell and every part of your body, and therefore they're all dissolved in the liquid part of the blood. And that can tell doctors whether you're healthy or not, depending on the levels. An aqueous solution, therefore, is what we're going to be talking about in this class. It's one in which water is the solvent. Okay. I also think it's important to understand that when an ionic compound, in other words, a compound that is held together by ionic bonds, is dissolved in water, each ion is surrounded by a sphere of water molecules, which is called the hydration shell. So hopefully this makes sense to you. So this over here is the sodium chloride, table salt, right? So you have a chunk of salt in water, big, it's pretty typical sort of thing, for a class. Now, what's going to happen is the water, these little Mickey Mouse heads here, white ears and red face, are going to surround each one of these atoms that makes up the salt. Now, if you see what's going on here, see how that sodium is positive? Well, that means all the negative parts of the water molecule, in other words, the oxygen side of the water molecule, are going to be facing the positive sodium, because remember, oxygen is negatively charged, right? For the chlorine, same thing is going on, where the chlorine is negative, but look what happens. All the hydrogens, the positively charged part of the water molecule, are now facing the chlorine atom. So what this does is it essentially cancels the charges out and allows all of these sodiums and chlorines to pull away from the bonds that they made to form salt. So that means you have sodium in your blood or in a liquid, right? And now you have chlorine in your blood or in a liquid. Hopefully that makes sense, and we'll talk about that more for bigger molecules in the next presentation.